Howdy, students. Let's talk about dice, or as I like to refer to them, the devil's bones. If you roll 2 dice many times, you can figure out the frequency within which each number comes up. You'll find that you roll a 2 about 3% of the time, a 3 about 6% of the time, and a 7 about 17% of the time, and so on. We can plot these up as a probability distribution. This is just a graphical representation of the table. It shows, for example, that 7s occur about 17% of the time. This plot doesn't tell me what any particular roll of the dice will be, but it does provide me with a lot of information about what the next roll could be. It tells me that there's a 0 chance of rolling a 13. It also tells me that rolling a 7 is about 6 times more likely than rolling a 2. And if I roll the dice many times, I'll get this probability distribution. Now you're probably saying, what does this have to do with climate change? The answer is that we can think of climate and weather just like we think of the dice. This is a probability distribution for the daily high temperature for Ellington Field near Houston during September in the 1970s. This is analogous to the probability distribution for rolling dice, and it tells us the probability that any particular high temperature will occur. It tells us, for example, that the most likely daily high temperature over this period was 32 degrees Celsius, which occurred on 19% of the days. But it doesn't tell us anything about the actual high temperature on any particular day. Weather, on the other hand, is the exact state of the atmosphere at any particular time. Here are the high temperatures for Ellington Field for the first few days of September 1970. You can think of each of these values as being a single roll of the weather dice that have a distribution determined by the climate in the panel on the left. So climate and weather are related but different concepts. You can think of climate as being the statistics of the weather. Or you can think of the climate as determining the range and probability of the daily weather. Climate and weather are important for different things. For short-term decisions, weather is often more important. Should you take an umbrella tomorrow? Should you dress for cold weather? Should you move your outdoor party scheduled for this weekend indoors? Should you go skiing this weekend? You look at the weather forecast to make those determinations. For longer-term decisions, it's usually climate that matters. Imagine that you're organizing an outdoor annual music festival in your hometown. In this case, you're interested in climate. You want to find the time of year when the weather is likely to be good. Temperatures not too hot or cold, weather likely to be dry, things like that. So let's think about having such a festival in College Station. You probably want to pick a month that has pretty mild temperatures. April or November both look pretty good, with average highs in the 70s and average lows in the 50s. But April has, on average, less rain, so that may tip the scales towards that month. Now, this analysis of the climate doesn't tell us what the actual temperature will be when the festival takes place. It just tells us the probabilities of weather. If you're unlucky, the weather could be awful, but if you're lucky, it will be terrific. Now, it's worth pointing out that climate is really made up of many factors, and who you are determines what part of the climate system you care about. In our music festival example, we obviously care about temperature and rainfall, but we don't want to pick a time of year when there are a lot of thunderstorms that bring lightning or strong winds, both of which could be a serious hazard to the attendees. It's also worth pointing out that climate is more than just the average. The annual average temperature in College Station is 26 degrees Celsius, 79 degrees Fahrenheit, which sounds fantastic. But we know that's an average between mild, comfortable winters and pretty miserable summers, with temperatures frequently approaching 40 degrees Celsius. We'll come back to this in Chapter 9, when we talk about the impact of weather and climate. And much of the bad things that weather brings comes from extremes. Extreme temperatures, extreme rainfalls, extreme sea level, etc. So this brings us to climate change. Let's revisit our climate dice analogy. This is the probability distribution I showed you earlier for the outcome of rolling 2 dice. It says the odds of rolling a 7 is about 17%. Let's imagine now that I give you a new set of dice and you roll them a bunch of times, and this is the distribution you find. If we eliminate the possibility that this is a statistical fluke by rolling the dice enough times, then you can conclude the dice have changed. With these new dice, you have a different expectation of what you'll roll. Obviously, you're more likely to roll a high number and less likely to roll a low one. For example, you roll a 10 with the original dice about 8% of the time, while you roll a 10 about 16% of the time with the new dice. The new dice also roll a 13 about 3% of the time, a value not possible with your original dice. This is a good analogy for one way to view climate change. Here's a schematic temperature distribution for some climate regime. If the climate warms, then this distribution shifts to the right. You'll note that in this warmer climate regime, you are far more likely to experience hot temperatures. In fact, there are some temperatures that are so hot they never occur in the previous climate. This is rolling a 13. Similarly, in the warmer climate, cold temperatures occur less frequently. Let's now look at some data. Here are probability distributions for September daily high temperatures during the 1970s in blue and the 2010s in orange. As before, temperatures were obtained near Houston, and the 1970s distribution was the same one I showed you earlier. As you can see, the distribution has shifted exactly as I described a minute ago. This is climate change. In the 1970s, the average daily high temperature was 30.4 degrees Celsius. In the 2010s, the average daily high temperature was 31.9 Celsius. In the 1970s, about 3% of the days had high temperatures above 34 degrees Celsius. In the 2010s, 15% of the days exceeded 34 degrees. That's a dramatic increase. In the 1970s, daily high temperature never exceeded 37 degrees Celsius. In the 2010s, 1.7% of these days had temperatures in excess of that threshold. The fact that temperatures that never occurred in the 1970s are now occurring is like rolling a 13 with a pair of dice. You know the dice have changed. Finally, we also see cooler daily maximums occurring less often. In the 1970s, 27% of the days had high temperatures below 29 Celsius. In the 2010s, only 11% did. Thus, the climate has changed. We are loading the climate dice. And because climate is the statistics of the weather, this means the weather is also changing. In the next chapter, I'll show you a lot more data demonstrating that the climate dice are indeed changing. And in chapter 7, I'll show you that human activities are responsible for these changes. And now, your moment of climate versus weather.
Well, whatever happened to global warming, eh?
Stop. From October the 1st, if you say whatever happened to global warming, eh? Whenever it's a bit cold or wet, you could be cooling off in a prison cell. This leaflet is being sent to every household in Britain. You have until September the 30th to learn the difference between climate, a long-term trend averaged over many years, and weather, which is what's going on outside the window right now. Make sure you study it, because if you don't, the next shower you get caught in could be in the prison wash block.
Can you look at this weather, eh? Still, I'm sure it'll all average out statistically to indicate a long-term warming trend.
Global warming quips. Get acclimatized.